In July of 2016, a spacecraft the size of a basketball court crossed into the most dangerous radiation zone in the solar system. And what it sent back a few months later made mission scientists go quiet in a meeting that was never meant to be public. You are about to hear what was in that photo, why NASA took months to say anything official about it, and why, even now, some of the world's top planetary scientists still cannot agree on what it means. By the end of this video, you will understand why a single image from Jupiter changed the way we think about the largest planet in our solar system, and why the silence that followed it was almost as strange as the picture itself. Jupiter is not just the biggest planet orbiting our sun. It is bigger than every other planet combined, with room to spare. If Earth were the size of a grape, Jupiter would be the size of a basketball. It has no solid surface to stand on. It is a giant ball of gas, and deeper down, strange forms of matter that barely exist anywhere else in the universe. For centuries, we only saw its outer face, the swirling bands of orange, white, and red that made it famous. We assumed for a long time that we understood the basic shape of the storms up there. Then, in 2011, NASA launched a spacecraft named Juno, and Juno was built to do something no mission had done before. It was designed to fly closer to Jupiter than anything in history, to slip beneath the clouds in a way no camera ever had, and to send home a level of detail nobody was fully prepared for. Juno reached Jupiter in the summer of 2016, right on schedule, and it settled into a long, looping orbit that carried it from far outside the planet's radiation belts down to just a few thousand miles above the clouds, closer than any spacecraft had ever dared to go. On board was a camera called JunoCam, and here is the part most people do not know. JunoCam almost was not included on the mission at all. Engineers considered it a bonus, a nice-to-have for public interest, not a serious scientific instrument. Nobody expected the pictures it sent home to become the center of a real scientific mystery. Two questions were quietly building inside the mission team from the very first orbit. What is actually happening inside Jupiter's storms, far below what any camera had ever captured? And why did some of the earliest images from Juno's camera get held back longer than anyone on the outside was told? The first close pass, called Perigove 1, happened in August 2016, and the raw images did not come out right away. There was a gap. Not a huge one, but enough of one that space forums and amateur astronomers noticed and started asking questions online before NASA said a word. When the pictures finally appeared, they showed something that did not match the smooth, almost cartoonish stripes we all grew up seeing in textbooks. Up close, Jupiter's clouds looked like oil paint dragged across a canvas by a violent hand, folding into storms within storms, some no bigger than a country, others larger than our entire planet. It was beautiful, and it was strange, and it was only the beginning. Imagine being one of the scientists in that first briefing room, watching a raw image load line by line on a screen, and realizing that the models built over decades did not fully explain what they were looking at. That is the feeling this story is built around, because as Juno kept orbiting, kept diving low and pulling back out, the pictures got stranger, not simpler. And that is where this mystery really begins to climb. Before we get to the poles, it helps to picture what Juno's orbit actually looked like, because the shape of that path is part of why these discoveries took so long to surface. Unlike earlier missions that circled Jupiter from a safe distance, Juno was placed on a long, elongated loop that carried it from millions of miles away, out past the orbit of some of Jupiter's smaller moons, all the way down to a close pass just a few thousand miles above the cloud tops and then back out again once every few weeks. Each close pass lasted only a matter of hours, a narrow window in which every instrument on board had to work at full capacity before the spacecraft swung back out into safer territory, away from the radiation that would otherwise cook its electronics. That meant every single photograph, every magnetic reading, every gravity measurement came from brief, precious slices of time, pieced together slowly, orbit after orbit, into the larger picture scientists eventually released to the public. It is part of why announcements about Jupiter often trail the actual flybys by weeks or months. The data has to survive the trip home, get sorted, checked, and cross-referenced against dozens of previous passes before anyone can say with confidence what it actually shows. The first jump in strangeness came from Jupiter's poles. Nobody had ever photographed them clearly before Juno, because every previous mission had approached from angles that only showed the equator and the familiar striped belts. When Juno's camera finally looked straight down at the North Pole, scientists expected something like a larger, messier version of the belts they already knew. Instead, they found a cluster of cyclones, arranged almost like the petals of a flower, one enormous storm sitting in the center with 8 more circling around it in a near-perfect ring. At the South Pole, the pattern repeated, but with 5 circling storms instead of 8. These cyclones were each roughly the width of the continental United States, spinning for years without merging into one another, without drifting apart, holding a strange and stable formation that nothing in the existing atmospheric models had predicted. To this day, the exact reason those storms stay locked in that pattern instead of colliding is still being studied, and scientists will tell you plainly that they do not have a complete answer. Then came the temperature data, and this is where things got personal for a lot of researchers, because it touched something they thought was settled. Jupiter's moon, Io, the most volcanically active body in the entire solar system, constantly spews sulfur and other material into space. Some of it gets pulled toward Jupiter and forms a thin, superheated layer high in the atmosphere. Juno's instruments picked up something odd about how that heat was distributed, hot patches appearing and fading in ways the standard models struggled to fully explain. On its own, that might sound like a small technical detail. But paired with the pole cyclones, it started to build a picture of a planet whose upper atmosphere behaves in ways that are far less predictable than anyone assumed going into the mission. Here's a number that tends to stick with people. Jupiter's Great Red Spot, that famous giant storm that has been watched by telescopes since the 1800s, is a hurricane wider than Earth itself, with wind speeds that can exceed 400 miles an hour. For a century and a half, we assumed it was a relatively shallow feature sitting on top of the clouds like a scar on the surface of the planet. Juno's instruments, using microwave sensing that could look beneath the visible cloud tops, found that the storm's roots reached down at least 200 miles into the planet, and possibly much deeper. Picture that for a second. Not a storm on the surface of Jupiter, but a storm that reaches down further than the deepest point in Earth's oceans. Still churning, still alive, more than 150 years after we first started watching it from the ground. And the Great Red Spot itself has been shrinking. Measurements going back to the 19th century show it was once wide enough to fit 3 Earths across. Today, it is closer to the width of 1.5. Nobody fully agrees on why. Some scientists think it will stabilize at a smaller size and continue for centuries more. Others think we may be watching the slow decline of a storm that has outlived every human observer who ever studied it, and could someday break apart entirely. We genuinely do not know which future is coming. But that wasn't the strangest part. Not even close. As Juno's orbits continued through 2017, 2018, and into the years after, scientists monitoring Jupiter's magnetic field noticed something that did not fit at all. Jupiter has by far the strongest magnetic field of any planet in our solar system, roughly 20,000 times stronger than Earth's. Scientists expected that field to be relatively smooth and even across the whole planet, similar in principle to how Earth's magnetic field wraps around us. Instead, Juno's data revealed a strange, powerful, localized patch of intense magnetism near Jupiter's equator, an anomaly so distinct that researchers nicknamed it the Great Blue Spot, even though it is invisible to the human eye and only shows up in magnetic readings. This blue spot behaves almost like a bruise in the planet's magnetic field, a place where something deep inside Jupiter, possibly in the churning metallic hydrogen layer far beneath the clouds, is generating a magnetic signature unlike anywhere else on the planet. Understanding why it exists means understanding how Jupiter's interior actually works, and that interior remains one of the most difficult things in the entire solar system to study, because no instrument we have built can see directly into it. There was another discovery buried in Juno's data that took scientists completely by surprise, something involving lightning. We have known since the Voyager missions in the 1970s that Jupiter has lightning, flashing inside its clouds much like storms on Earth. But Juno's instruments picked up a strange new kind of flash, one that seemed to originate much higher in the atmosphere than any lightning should be able to reach, in a layer far too cold for regular thunderstorms to form. Scientists eventually worked out an explanation, though it took years to piece together. High above Jupiter's main cloud deck, ammonia mixes with water in a way that lowers the freezing point of the resulting droplets, allowing a strange form of slushy hail to form and generate electrical charge. At altitudes nobody expected lightning to survive. Researchers gave this phenomenon an almost playful name, calling the strange hailstones mushballs, because of how they form and fall through the atmosphere, scavenging ammonia as they sink toward the deeper, hotter layers of the planet. It sounds almost too strange to be real, and yet it explained something that had puzzled scientists since the very first lightning detections decades earlier, a missing layer of ammonia in Jupiter's atmosphere that nobody could previously account for. It had not disappeared. It had been raining down, frozen inside slush the entire time, hidden from every instrument until Juno finally caught it happening. This is the point in the story where you have to stop and think about scale for a moment, because it is easy to hear numbers like these and let them slide past without really landing. Jupiter is so large that if you took every other planet in our solar system and combined their entire masses together, Jupiter would still outweigh all of them by more than double. Its radiation belts are so intense that they can fry unshielded electronics within hours, which is why Juno had to be built with a special vault of titanium just to survive long enough to complete its mission. We are talking about a planet so violent, so massive, and so strange in its interior that a spacecraft essentially had to be armored like a tank just to take its picture up close. And still, after all of that engineering, after years of close passes, the deepest layers of Jupiter remain a mystery we can only guess at using indirect measurements, gravity readings, and magnetic field maps. Now here is where the human side of this story gets interesting, because it was not just the storms and the magnetic field that raised eyebrows. It was a photograph. During one of Juno's close passes in the years following its arrival, JunoCam captured an image of a specific region near Jupiter's equator that mission scientists internally referred to as a chaos region, a patch of atmosphere where the normal cloud bands broke down completely into a tangle of folds, filaments, and swirling white material that did not match any weather pattern in the archive of images collected up to that point. The raw image was processed by the public image team, as JunoCam images always are, since NASA had made a point of releasing most of its raw data for citizen scientists and amateur image processors around the world to enhance and study. But this particular set of images sat in the public pipeline for an unusually long stretch before an official statement described what the region actually was. Space forums picked up on the delay almost immediately. People noticed dates not lining up with the mission's usual fast turnaround. Was it just scheduling? Was it a genuine gap in understanding where the scientists needed real time to determine what they were even looking at before making a public statement? NASA's own explanation, when it eventually came, was straightforward, describing ongoing analysis and caution about releasing interpretations before the data had been properly reviewed. But the delay itself became part of the story online, feeding speculation that spread faster than the science ever could. There is one more layer to this part of the story worth sitting with, and it involves Jupiter's moons rather than the planet itself, because Juno's cameras did not stay pointed only at the clouds below. During its extended mission, Juno swung close enough to Ganymede, Jupiter's largest moon and the biggest moon in the entire solar system, to capture the most detailed images of its icy surface in over 20 years. Ganymede turned out to be strange in its own right, the only moon in our solar system known to generate its own magnetic field, strong enough to create auroras near its poles, glowing curtains of light not unlike the northern lights here on Earth, except playing out on a frozen moon nearly 400 million miles away. Around the same time, instruments studying Jupiter's icy moon Europa picked up hints of water vapor plumes erupting from cracks in its frozen shell, tentative evidence, still debated among scientists, that liquid water beneath that ice might occasionally vent into space. None of this proved life exists out there. Nobody serious in the scientific community has claimed that. But it added another thread to the same underlying theme running through this entire mission. Every time we look closer at the Jupiter system, we find more motion, more energy, and more open questions than the quiet, static picture we grew up with ever suggested. Let's take a breath here and go back to where we started, because this is the moment to remember the promise from the very beginning of this video. We told you that a photograph came back from Jupiter, and that NASA's response to it took longer than anyone expected. That chaos region is the closest thing to that photograph, and the pause in explaining it is the closest thing to that silence. Whether that silence was simply careful science, or something that reveals how uncertain even our best experts still are about this planet, depends on how you look at the evidence. We're going to walk through what the leading explanations actually say, and let you decide which one feels closest to the truth. The most widely supported explanation among planetary scientists is what is sometimes called the storm collision theory. Jupiter's atmosphere is in constant motion, with bands of gas moving in opposite directions at incredible speeds, some regions rushing eastward, others westward, right next to each other. Where these opposing currents meet, turbulence builds, and every so often two or more storm systems collide and tear each other apart, creating exactly the kind of chaotic, folded pattern captured in that image. Under this explanation, the region was not evidence of anything hidden or unusual, just a rare but natural collision of weather systems, made stranger looking than usual because of the angle and lighting when JunoCam happened to capture it. Many scientists find this the most likely answer, and it fits comfortably within existing models of how Jupiter's atmosphere behaves. A second theory focuses on deep upwelling, the idea that material from far below the visible cloud layer, possibly carrying heat or chemical signatures from Jupiter's interior, was pushing upward and disrupting the normal cloud patterns from underneath. If true, this would mean the chaos region was not just a surface event, but a rare window into deeper processes, usually hidden from view, something closer to Jupiter briefly showing us a piece of what lies beneath its clouds. This theory is harder to confirm because it relies on inferring what is happening below a layer we cannot directly see, using only the disturbance it leaves behind on the surface. Some researchers find it compelling specifically because the chaos region appeared close to areas where Juno's gravity and magnetic instruments had already flagged unusual readings, including the region near that great blue spot anomaly. Others argue the overlap could simply be coincidence, given how much of Jupiter's atmosphere is turbulent in general. A third, more cautious position, held by a number of atmospheric scientists, is simply that our models of Jupiter's weather are still incomplete, and that features like this chaos region are exactly the kind of thing we should expect to keep finding as our instruments improve. Under this view, there is no deep mystery requiring a special explanation. There is only the humbling reality that Jupiter is far more complex than the smooth, striped ball many of us grew up picturing, and that every close look we take reveals texture and detail that our older models simply did not account for. This explanation gets far less attention online because it does not offer a dramatic answer, but many career scientists consider it the most honest one because it does not require inventing a cause. It simply admits that the planet is more complicated than we assumed, and that admitting the limits of our knowledge is part of real science. There's a fourth angle worth mentioning, one that comes less from atmospheric scientists and more from the specialists who study Jupiter's gravity field. As Juno passed close to the planet on each orbit, its radio signal back to Earth shifted in tiny, precise ways caused by the pull of Jupiter's gravity, and those shifts let scientists map out how mass is distributed inside the planet layer by layer, without ever seeing beneath the clouds directly. That gravity data revealed something unexpected, that Jupiter's core is not the small, sharply defined ball of heavy material many models had assumed for decades. Instead, it appears to be diffuse, a fuzzy, partially dissolved core blending gradually into the surrounding layers of metallic hydrogen, rather than sitting as a distinct object at the center. One leading idea is that a massive collision, early in the solar system's history, smashed a large planetary body into the young Jupiter and partially mixed its core into the surrounding layers, leaving behind the blurred structure we detect today. If that is correct, then some of what Juno has been capturing on camera, the strange upwellings, the unexpected chaos regions, may be surface echoes of a violent ancient event still settling out inside the planet after more than 4 billion years. It is a dramatic idea, and it remains one of several competing explanations, rather than a settled fact, but it shows just how far a single photograph can ripple outward once scientists start asking what could possibly explain it. What makes this hard to settle is that none of these explanations fully rule out the others. The storm collision idea and the deep upwelling idea are not mutually exclusive, since a collision at the surface could easily be triggered or intensified by material pushing up from below. And the honest admission that our models are incomplete applies no matter which specific mechanism turns out to be correct. This is the tension every serious mystery in science eventually reaches, the point where the data supports more than one story, and where scientists have to sit with genuine uncertainty rather than pretending they have it all figured out. That tension, more than any single photograph, is what kept this story alive in scientific circles for so long. There is also a simpler, more human explanation for why the delay felt significant, one that has nothing to do with cover-ups. Juno's mission produced an enormous volume of data, more than any prior Jupiter mission by a wide margin, and the team analyzing it was small compared to the scale of what they were reviewing. Papers describing new findings often go through months of internal review before anyone outside the immediate team sees a polished explanation, because scientists are cautious about publishing conclusions that later turn out to be wrong. In an era where every image gets scrutinized online within hours of release, that normal, careful pace of science can look, from the outside, like reluctance or secrecy, even when it is really just scientists trying to get the answer right before speaking publicly. It is worth holding both of these truths at once. The delay was real. The explanation for it may be far less dramatic than the internet wanted it to be. Here is where we reach the heart of the story, the single fact that ties everything together. The reason Jupiter keeps producing moments like this, images and readings that outpace our ability to explain them in real time, comes down to one basic truth about the planet itself. Jupiter formed first, before any other planet in our solar system, gathering an enormous share of the leftover material from the young sun's disk of gas and dust. That head start gave it a mass so large that its interior pressure and temperature climbed to extremes no other planet in our solar system reaches. Conditions so intense that hydrogen, the simplest element in the universe, is squeezed into an exotic metallic state that conducts electricity like a metal despite still technically being a gas at the surface. That metallic hydrogen layer, churning far beneath the clouds, is almost certainly responsible for generating Jupiter's overwhelming magnetic field, the same field behind that great blue spot anomaly. In other words, the storms on the surface, the deep magnetic patches, and the chaos region in that photograph may all trace back to the same underlying cause, a planet whose interior operates under conditions so extreme that our models, built mostly from studying much smaller, calmer worlds like Earth, simply were not built to fully predict them. Jupiter is not hiding something from us in the way a person might hide a secret. It is simply operating on a scale and under pressures so far beyond anything in our direct experience that catching up to it, fact by fact, image by image, is going to take decades, not years. Think about what that actually means for a moment. Every planet closer to the sun than Jupiter, including Earth, is built mostly from rock and metal, dense material that came together after the fierce early sun burned away the lighter gases nearby. Jupiter formed far enough out, and early enough, that it managed to grab hold of huge amounts of hydrogen and helium before that material could drift away or get swept up by the sun itself. That single accident of timing and position is the reason Jupiter is what it is today, a planet with over 300 times the mass of Earth, wrapped in a churning, electric, endlessly shifting atmosphere, hiding a core that may still be settling from a collision older than complex life on our own world. Every strange reading, every unexplained storm, every delayed explanation, all of it traces back to that one basic fact about how this planet came to exist in the first place. That is the real reason the response to that photograph felt slow. It was not silence born from fear of what was found. It was the sound of scientists trying to describe something genuinely at the edge of human understanding, using careful language instead of easy answers. Because Jupiter has, again and again, proven that easy answers about its interior are usually wrong. Step back for a moment and think about what it means that a planet sitting more than 400 million miles from where you are reading this can still surprise the people who have spent their entire careers studying it. We built a spacecraft, armored it against radiation strong enough to destroy ordinary electronics, sent it across the solar system for nearly 5 years, and flew it closer to Jupiter than anything in human history. And even with all of that effort, all of that engineering, all of that expertise, the planet still handed us more questions than answers. There is something genuinely humbling in that, and something quietly hopeful too. It means the universe has not run out of mysteries for us to chase. It means the smartest people on this planet, with the best instruments we have ever built, are still standing at the edge of what we understand, looking out at a gas giant and admitting, honestly, that they do not have the whole picture yet. Juno's mission has continued to extend far beyond its original plan, diving past not just Jupiter but its moons, capturing new images of Europa's icy surface and Io's volcanic eruptions, each pass adding another piece to a puzzle that keeps growing rather than shrinking. Every time we think we have finally mapped the shape of what Jupiter is, the planet offers a new detail that does not quite fit, a new anomaly that sends scientists back to their models, a new reminder that we are still, in many ways, just beginning to understand our own solar system. That, more than any single photograph or any single delayed press release, is the real story here. Not a cover-up, not a secret being kept from you, but the ongoing, unfinished work of people trying to understand a planet that is simply bigger, stranger, and older in its violence than almost anything we have ever tried to study up close. So the next time you look up at the night sky and spot that steady, bright point of light that is Jupiter, hanging there quietly among the stars, remember what is actually happening inside it. Remember the storms taller than our planet, the magnetic bruise no one can fully explain, and the photograph that made an entire team of scientists pause before they spoke. If this story pulled you in, stick around and subscribe, because there are more of these hidden corners of the solar system waiting to be explored, and I would genuinely love to hear in the comments which part of this one surprised you the most.